Hey, it's Dr. J. Today we're going to learn a couple more rules to add to our 7 differentiation rules, or the rules of the derivative. We're going to talk about the product and the quotient rules today. So you might recall that we have, I guess, what I called rules number 6 and 7. If we were keeping track of the numbers, that said if you had the derivative of the sum, then you could just take the derivative of the first function and then the derivative of the second function and then add those two derivatives together. Yeah. In other words, in words, we say the derivative of a sum is equal to the sum of the derivatives. So these are rules 6 and 7. The same thing was true for the difference. So the derivative of a difference or subtraction is equal to the difference of the derivatives. Pretty straightforward. Yeah. Unfortunately, this is not true for products. So if you had the product of two functions and you wanted to take the derivative, it is not this simple. This is not true. It's not this simple. So if it was that simple, I would have given it to you along with the other rules. But because this rule will not be that straightforward, also the quotient as well. So if I said the derivative of f of x divided by g of x, it is not just simply f prime on the numerator and g prime on the denominator. Again, that would be too easy. But you know the old saying, if it's too good to be true, it's because it's not true. So these statements are not true. So we need to develop some new rules for products and quotients, and they just deserve their own treatment. And so that's what we're going to do today. Let's start with the product rule. All right. So if we want to take the derivative of the product of two functions, sometimes I use round or curved parentheses, and sometimes I use square brackets. Sometimes I don't use them at all, but I'm going to be very formal here. I'm going to write it exactly the way it's written in the text. The derivative of the product is equal to the derivative of the first function, f, times the second function, g, without a derivative, plus the first function without a derivative times the derivative of the second function. So this is called the product rule. Okay. We could see an example of this. So if y is equal to x squared plus 9 times 6x cubed plus 4, then dy dx. So this is f this one's G. And the parentheses mean they're being multiplied. These parentheses here. We're multiplying them. So this would be the derivative of x squared plus 9 times 6x cubed plus 4. Again, so this is G and this is F. So first we do F prime. So that'll be 2x. That's F prime. I'm just going to write F prime. I'm not going to write the whole of x. And then we do G. 6x cubed plus 4. Plus. So plus. Now you do F. Or now you write F. X squared plus 9. So there's F. And then you do G prime. And then you write G prime. So G prime would be 18x squared. For shorthand, we just write F prime G plus F G prime. That's just the shorthand way to memorize all of this without writing all the x's. The x's are just to indicate that the variable is x. We might switch variables at some point, so it's important to keep track of what variable we're using. As long as it's obvious that the variable is x, then writing it really doesn't help the problem at all. So this is the derivative unsimplified. I like to simplify a simple form or simplified form. So we'll just clean this up a little bit. That'll be 12x to the 4th plus 8x plus 18x to the 4th plus 9 times 18. What's that? 162x squared. I ran out of space. So simplified answer dy dx is 30x to the 4th, because I'm combining the 18 and the 12. Those are both x to the 4th. Then 162x squared. The order doesn't really matter, but I like to be neat about it. If I'm going to go through the trouble of simplifying, it's nice to have it in the most simple form, which is typically from largest to smallest, or what's called descending. You know that, descending powers. So that's the product rule. I should point out that if you just took the derivative of f, it would be 2x, right? Because the 9 is a constant, so that becomes 0. So it would just be 2x. And if you just took the derivative of g, that'd be 18x squared, right? So the idea at the beginning that I said, well, it's just not that easy. If you tried that, if you said, well, why not? Sometimes you might want to challenge me and say, well, why can't I just make it easy and get the right answer? Well, clearly you will just not get the right answer. It'll clearly be incorrect. That will not actually be the derivative, right? Derivative is much more complicated. It's got many more terms. Right? That would only be two terms, or two, actually it'd be two factors. They'd be multiplied together. And when you multiplied them, you would get one term for the final answer. And this has three terms, right? Three distinct terms. Sometimes it might even have 4 or 5 terms, depending on how large the polynomial is. It will never be as simple as just one term. That's just an unreasonable expectation. Okay. Now the cool thing about the product rule is multiplication with addition. Yeah, and both operations are commutative. So what I'm trying to say is, if you write it down incorrectly, it may not be incorrect. So the way I memorize it is f prime times g plus f times g prime. Yeah. But this is also the same as f times g prime plus g times f prime. This is also correct. This is also correct. F prime times g plus g prime times f. So there are many different ways to write it that may all be correct. Yeah. Let me do one more. How about g times f prime plus g prime times f. Yeah. So there are many correct forms. The key to the product rule is not the order, right? The order really doesn't matter. You can change the order of multiplication, and you can change the order of the addition, and you will still get the right result. The key is that each factor has one derivative in it, yeah, and each factor has one of each function. So you've got one f and one g. So there are many different arrangements of the product rule that'll all be correct. Okay, so I don't, require you to memorize every single correct form. I've run out of board space here, but I could probably write it 3 or 4 different ways and still be correct. Okay, so I just want to keep that in mind. I might occasionally change the order in which I do it and still get the same result. Let's try another one. So we have h of x is 10 times the square root of x times ln of x. Find h prime of x. Okay, so the shorthand notation is just f and g. All right, so there's a dot, so it clearly indicates the separation between the two functions. Sometimes we do not write that dot. You've seen me omit it many times in the past. If the dot is omitted, then it is implied that the two functions are being multiplied. I guess you could put a second dot here between the 10 and the square root. The reason why I'm not doing that is because 10 is a constant, and it's going to come out of the derivative anyway. So I just ignore that for now. Okay, so a quick sort of memory, good idea. You don't have to look at your notes. You want one f prime and one g, and then you want one g prime and one f. And again, the order doesn't really matter because you're multiplying, and similarly, the order of the addition doesn't matter as well. You could do it in a reverse order and still get the same result. All right, so f prime, the derivative of 10 square root of x is 10 times 1 over 2 square root of x. Maybe I'll review that. It's been a while since my last video, maybe it's been a couple days, maybe it's been the weekend. I don't know how long it's been since you've seen the last video, but so let's just review this really quickly. That would be 10x to the 1/2 power, which would be 10 times 1/2 x to the negative 1/2, which would be 10 times 1 over 2 square root of x. All right, so this is f, and then this is f prime. Quick little review. All right, so f prime is 10 times 1 over 2 square root of x. All right, and then now g. What do we got? G is ln of x. That's g. All right, plus g prime. So g prime is 1 over x. Right. So let's do another review. This was just one of those rules. If g is ln of x, then the derivative of ln of x is just 1 over x. I think it was rule number 5. Or maybe I called it rule number 5 star. It was special case. I don't know if that looks like a star or not, whatever. Yeah. The derivative of a natural logarithm. All right, so that's your g prime. And then finally, the f is just back to being 10 square root of x. Be careful with fractions. These technically are fractions, these two terms, with an invisible 1 in the denominator. That's to keep your fractions lined up. So you're going to have 10 ln of x over 2 square root of x plus 10 square root of x over x. So when you multiply these, be careful. The numerators multiply and the denominators multiply. And if you get sloppy, they start getting off balance with each other. You might multiply the wrong things, you know. Or you might not, I don't know. All right, this is interesting here. I want to simplify this as much as possible. Here's an easy simplification. 2 goes into 10 5 times. I really could have done that a few minutes ago. I was just waiting until now. But here's a not so obvious simplification. Maybe not so obvious that you can combine these x's by rewriting the square root as a 1/2. And then this is a 1. Yeah, x is really just x to the 1. And then you can subtract these. I usually subtract the largest one minus the smallest one. So it'll be 1 minus 1/2 will give you 1/2. Now you could go the other way. You could do 1/2 minus 1. That would still be correct, but then you'd get negative 1/2 and you'd have an extra step. But it wouldn't be wrong. It would still be correct. So h prime of x is equal to 5 ln of x plus 10 all over the square root of x. See how the denominators are both the same? They might not look the same, but those are the same. Yeah, this is the square root of x on the left, and this is also the square root of x on the right. So you just write it one time. There you go. That's your final answer. Well, one issue with the formula or the rule f prime g plus g prime f, or however you want to memorize it, is the letters. You can never trust a name or a variable for a particular factor or term. So this function is already called f. Yeah. So you don't really want to use f equals fg. You see how confusing that would be if you call this f and you call this g, then basically you're saying f of x equals f of x times g of x, right? That's bad. Yeah, you don't want to do that. You don't want to name a function f and then have an f as part of the function that's named f, right? It's sort of chasing your own tail. Bad idea. All right, so don't do that. You really shouldn't be attached to the letters f and g. You should be flexible and maybe use other letters. So another version of the product rule is u prime v plus v prime u. In fact, you can use any letters. You could say a prime b plus b prime a. You could say p prime q plus q prime p. You could do it any way you like. The most common letters for functions are f and g. I might introduce u and v as this probably the second most common, but a and b, not very common. P and q, yeah, they show up. We've seen p and profit. We haven't seen q yet, but q might be a nice variable to hang on to for later. One of the problems with q is people are sloppy and they write it like this, and it might end up looking like a g. So you have to have really good writing to make sure your q's don't look like g's. But anyway, I'm going to use u and v. All right. So the derivative f prime is going to be u prime v plus v prime u. So u prime, it's going to be negative 24x squared plus 14x to the 6th. That's u prime. And then v, keep v exactly the way it is, plus v prime. So v prime would be 5e to the x minus 4. Remember, e to the x is one of those special derivatives. The derivative of e to the x is just e to the x. So that term doesn't change. The derivative of 4x is just 4. And then u, and u stays exactly the same way. You may leave this answer unsimplified. A couple of reasons. One is that it doesn't really get much better when you simplify it. So, but there's another reason, and that's later in the chapter. I'm going to show you how by leaving it unsimplified, you can do something nice with it that is harder to do once you simplify it. So basically, I'm just saying, hang on to this. It's going to look terrible for a minute. It's going to require a lot of typing and a lot of parentheses. Now, you may leave it unsimplified. If you want to simplify it for an academic experiment or exercise, you can go right ahead and do that and see what it looks like. It's going to just be another mess of jumbles of letters and numbers. But in the next chapter, it'll probably be in the next chapter, I'll show you how leaving it unsimplified actually helps you solve a problem that we're going to see in the future. So occasionally I'll tell you, just go ahead and leave it unsimplified. All right. A couple more product rules. I don't know. Example 4. G of x. Here's another one of those where the letter in the function is a letter you're already using. So there's our function called g of x. So same argument, right? If this is called g, then you don't want to call one of these guys g. Right? So just call them something else. Call this, I don't know, u and v or something. Or a and b or p and q or whatever you want to call them. Doesn't matter. You can even give them like human names, you know. I'm not going to. Okay. So g prime of x, the derivative of u is 8x minus 1, yeah, plus 0, yeah. Remember, there's an invisible 1 here in front of the x. So that's u prime. And then v. V is just ex. And then v prime. Hey, v prime is just ex also. So v and v prime are the same thing. Yeah, that's the magic of e to the x. E to the x is a one of the only, or probably the only function, I should just say it, it's the only function in which it is the derivative of itself. You take the derivative and it doesn't change. It just becomes the same value again. And then u. Okay. So u is the whole thing here. 4x squared minus x plus 5. And I want you to simplify this one. Simplify this one. So you're going to get 8x e to the x minus e to the x plus 4x squared e to the x minus x e to the x plus 5 e to the x Now we're going to combine these and put them in order. So we'll put this one first. That one goes first. We'll put this one second. So that'll be 7x e to the x. All right, I have an 8. And I've got an invisible 1 here, negative 1. So 8 and negative 1 is going to give me 7. And then here I've got a 5. And again, an invisible -1. So that's going to give me 4. And there's your answer. I will also accept this. You can write the answer in the same form as the question by simply putting, since they all have an e to the x, you can put that out in front. Same form as the original function. With the e to the x out in the front. Either one. I don't care. They mean the same thing. So that's the product rule. Now, the only thing that could get strange with the product rule is if I don't give you one of the functions. I lost count. 1, 2, 3, 4. Oh, this is 5. Right? Am I counting? 1, 2, 3, 4. Yes, this is 5. So sometimes I play this sort of hide and seek game with functions. I don't do it very often, but it's more of an abstract way of thinking about mathematics where you kind of have half the picture and you try to piece it together. Sometimes I do this with graphs or with tables. In this example, I'm doing it sort of in algebraic notation. So I've got f of x is x squared times h of x. H of 1 is 7. And h prime of 1 is 6. So I want you to find the derivative of 1. F prime of 1. So first, we're going to do this. We're going to find f prime of x using this definition. Right? So basically what we're saying is that f of x is a function that is x squared times another function. So let's use the product rule because there's a product. There's an invisible product right there. So the derivative of x squared is 2x times h of x plus h prime of x times x squared. That is the product rule. And I like to just say it in words, the derivative of the first function times the second function plus the derivative of the second function times the first function. It just kind of rolls off the tongue that way. So now to find f prime of 1, plug in 1 everywhere there's an x. So all of the x's then become 1s. Or whatever number is in the problem that you have. I rolled the dice and I got 1, so I could have done it for any number. So that's going to be 2 times 1 is 2. H of 1 is 7. H of 1 is 7. Plus H prime of 1 is 6. H prime of 1 is 6. And then 1 squared is just 1 again. So that's 14 plus 6. So the derivative is 20. And I'm going to go back to talking about business in a minute here, and this type of problem can be applied to a business type question. Not these exact numbers. I just made these numbers up to kind of do an abstract example, but in a concrete example or a real world application, the 20 might mean something, right? It could be $20, or it could be 20 units of production or profit. It could be money. It's probably money, but there are basically two things that we deal with in the business applications. We have quantity, how many things there are, and then we have value, what they're worth in terms of dollars. So this answer could mean something as it relates to the business applications. All right. So having said that, without any further ado, let's get back to business. In the last time we were together, we were talking about marginal analysis. So a quick review. Let's talk about marginal revenue. Remember, so R prime of X. I'm just going to do one example. It's called marginal revenue. But you have this concept for all of the applications: cost, profit, and revenue. You just add the derivative, and we call that the margin, or the marginal revenue. And R prime of n minus 1 gives us the marginal revenue earned by selling the nth unit, or item, or whatever it is that we're selling. We usually call them units. Sometimes we call them items. So if you want to know how much you're going to earn by selling the 25th, cookie or scoop of ice cream or gallon or whatever it is that you're making, widget, I like to call them widgets. If you want to know the 25th, well, then you back up one, you back up to the 24th, and you take the derivative. And that's called marginal analysis. It gives you the marginal revenue, right, of that next item. We call it the next item, or the next unit. I did an example where a company sells, I don't know what it was, cookies or ice cream or something. I'm just going to call them widgets because it really doesn't matter. And I'm constantly changing. I resist actually using, real things, but sometimes it just gets boring to always sell abstract things. So you might be doing your homework and I might, have a random, object that I've selected. I just don't feel like picking one today. So I'm just going to call it widgets. You can apply it to any of the problems that ask about revenue. And using a price demand function, so here's a question that we could not answer last time. Remember, this P is a lowercase p. You got to be careful when you write it. It's not profit, it's price. And this is a price demand function where the exponent is a variable. So in this particular price demand function, so price is the y and x is the demand. All right, I'm kind of in the way of it. The 500 is like the highest price that you would ever sell the item for. The problem with selling something for $500 is that nobody's going to buy it. Yeah. So we call that a prohibitive price. Yeah, it's so expensive that nobody buys it, right? Now, I don't know what these are. They're just called widgets, but whatever the heck they are, $500 is too much. And so this function curves down like this and approaches zero. The price approaches zero as the demand approaches infinity. All right, so that's how the price demand. And so in my previous lecture, we could analyze the price, right? We could do that. But for this type of function, we couldn't talk about the revenue yet. But now we can. With the product rule, we can find marginal revenue. So let's do that. Let's find the marginal revenue of this particular product, whatever it is, the widget. So recall, revenue, and I'm not taking a derivative yet, is equal to X times the price, or the price demand. So it's the number of units times the price demand function. That's revenue. That's the formula for revenue. And now we have an exponential price demand function. So 500 times 0.99 to the x. Right. Let's rewrite this with the constant out in front. Like that. And if you want, you can move the dot right here so that it's clear which function is our f and which is our g. So this is our f, and this is our g. You got to decide how you're going to split the two functions. It really doesn't matter as long as they each have at least one x, or they at least have they each have exactly one x. So you wouldn't want to split it so that one of the functions has two x's and then the other one has none. They each have to have one x. Otherwise, you can't take their derivatives. So this is called the revenue function. Right here. That's our revenue function. Now let's find the marginal revenue. So find the marginal revenue when the 71st unit is sold. So this is our N. So we want R prime of X. First, we're going to keep it as an X, and then we'll plug in a number in a minute. And I'll explain what number we want to pick. So R prime, that's our marginal revenue. It's telling us how fast, what rate is the revenue changing. All right, F prime. F prime is 500. F is 500X. Times G. G is 99 cents. That's what that means, 99 cents to the X power. Or 99 hundredths, or however you want to say it. 0.99. All right, so that's F prime and that's G. Maybe I'll write it out one more time. F prime and G. Okay, now we're going to do G prime. Now, G prime was tricky. It was one of those rules, and this is not E. This is a base A, I guess. So because it's not E, you have to add in the ln of 0.99. So all of this is G prime. All right. And then let me squeeze in F here. I'm running out of space. So we're going to squeeze in F here. There's F. So there's F. I just wrote it very small. I'll write it again in a second. I'll give myself some more room. So my R prime is 500 times 0.99 to the x power plus 500x times 0.99 to the x power times ln of 0.99. This is what we could not do in the last video. We could do this for easier, simpler functions, but we couldn't do it for this type of function because we didn't have a product rule in the last video. All right, so now we can analyze the revenue of more complicated structures. Now remember, this question is asking us for the revenue when the 71st item is sold. So n is 71. So n minus 1 will be 70. So that's what we're going to plug in. The derivative when 70 units are sold. And it's messy. So that is your sort of template for the answer. R prime of 70. All right, hold your horses. Hold on to your hats. All right, where do we start? It doesn't really matter. It's just going to be a big mess. Let's just do this first term. Do the exponential first, so 0.99. You're going to do y to the x button. And then to the 70th power. So that gives me, this is 0.99 raised to the 70th power. Then multiply it by 500 and go ahead and write that down. We are approximating, we will round to the nearest penny. I'm not going to round yet. I'm gonna put 4 or 5 decimals and I'll round later. I probably could have got away with 3 decimals, but I don't know. I'm just gonna put ... there. If you want to write the entire screenshot down, that's probably not a bad idea. All right, good. So we got that. Check. That one's done. Check. So now let's do this one. This one's gonna be a little trickier. Let's well, let's keep what we have. Now remember, so what you have on your screen represents the 500 and the 99 to the 70th, those two. So just multiply this by 70. You don't have to write it down again. Just multiply it by 70. And now you've got these first 3 terms done here. Now look how it got larger. 17,319 now. So the only thing you have to do now is the ln of 0.99. Now I always screw this up, okay, especially on a phone. All right, if I had my old standard scientific, I might be able to pull it off. So I'm afraid I'm going to screw this up, so I'm going to write this down. And then if I happen to lose it, I can always recover my data. It's like the way we used to save stuff in the old days. When I went to school, you had these little discs. You had to copy everything onto these discs in order to floppy disks, in order to make sure you didn't lose your term paper or your research or whatever you're doing. Now you've got these computers and phones and things that save everything, but I still have unresolved issues from the 90s. So, okay, so let's go. So I'm just going to clear it out. I'm afraid I'm going to get it wrong if I don't. And I'm going to do ln of 99 cents. So on my calculator, ln of 99 cents. It's a negative number, right? Whenever you take the logarithm of a number less than 1, you always get a negative, right? So that's this number here. Now I can multiply it by the number I have saved. So times 17,319.3531. All right, so that's negative 174.0653. And then I've got this number, 247.41932. It was adding, but because I'm adding a negative, it's going to be subtracting. So it's plus a negative. I'm just going to do subtracting 247.41932. And I get approximately $73.35. It rounds very nicely because the third digit is a 4. So it's just 35 cents. Or you say $73.35. Yeah, or $73.35. So that is the price, or that is not the price. Sorry, it's not the price. That is the revenue of the 71st item. I'm not going to ask it in this question, but you might be curious. That's how much revenue you're bringing in when you sell it, when you sell that next item, right? It should be very close to the price, because the price of an object is essentially equivalent to the revenue for that particular object, because you're not, selling another object. I mean, you're not, there's no cost in this formula. This is just for selling that one particular unit or object or item or whatever you want to call it. All right, really this example was really belonged in the marginal analysis lecture that I gave a while ago, or last time, I guess, if you're watching these in order. But it couldn't fit in with those others because we didn't have this rule yet. So I had to put this one off until today. Let's move on to the second half of this video, and that will be the quotient rule. Okay, so as was mentioned, the derivative of a quotient, in other words, a fraction of functions, it's called a quotient, function in the numerator, function in the denominator. It's not as simple as taking the derivative of the top and taking the derivative of the bottom. In fact, it's not that simple, so I'm not even going to write that down. All right, I don't want the false statement in the notes. Right. I mean, unless you want it in the notes, then write it f prime over g prime. Not true. It's a little bit more complicated than that. What it is it's f prime times g minus g prime times f over g squared. The whole function squared. That's why I use an extra set of brackets here. All right. And since this is subtraction, it is not commutative. So the order matters. If you change the order, oh no, did I write that in green? I don't know. My green screen. This arrow might be invisible to you. I don't know. Sometimes when I watch my videos, like, oh, I gotta throw away all my green pens. Yeah. The order matters. All right. So be careful. This is incorrect. If you do um, f g prime minus g f prime over g squared. This is false. All right, so be careful. I don't know why I put my big X there. Here, let's put it here. So this one's a little harder. You know, it's not quite as forgiving. If you screw up the order, you will get the wrong answer. Okay. Here's the way I remember it. All right. Whichever function is in the denominator must be g. So keep track of the denominator. The denominator must appear in the denominator squared, and then it must also appear as a derivative on the right-hand side. All right, so that's how you know whether it's correct. So you see over here, it did appear in the denominator. Yeah, g is still in the denominator, but the derivative is on the left-hand side, and this is subtraction, and so this is the reason why it's incorrect. You could do it this way. You could do g f prime minus f g prime. That would be okay. Yeah. And you could also do this. This is the way I do it. F prime g minus f g prime. And again, make sure the denominator is g. So personally, I either do it the first way I wrote it down, or sometimes I'll do it this last way. This one is okay. It's still correct. I don't think you'll see me do it this way. It's just one of the ones that I know it's right. I just don't do it that way. Yeah. I know I can do it that way if I want to, but I just don't. All right, I talked too much. Let's see. 1, 2, 3, 4, 5, 6. We're on example 7. Example 7, y equals the ln of x over x to the 9th power. So find the derivative, dy dx. All right, let's write our little shorthand here. Help us remember it. It's going to be f prime g minus g prime f over g squared. That's the shorthand. So you should memorize that. Shorthand memory. Okay. All right, let's do it. So we got, let's just do the g squared first. That's x to the 9th squared. Done. That's easy. All right. Don't do anything to the denominator other than square it. All right. Don't do the derivative. Don't modify it in any way. Just keep it the same. Okay, and so now let's follow the pattern. F is the numerator, so f prime is 1 over x. Should have that memorized. The derivative of ln is 1 over x. Then times g, x to the 9th. Now be careful, that x to the 9th is not downstairs, so sometimes you might want to put a little invisible 1 right there, like I said earlier, to keep things lined up. And then minus, So g prime is the derivative of the denominator. That's 9x to the 8th. That's g prime. And then times f is ln of x. And that's it. That's your answer. I'd like you to clean it up a little bit. I mean, there's only a couple of these that I just let you leave messy. This is not one of them. So that'll be x to the 8th. Yeah, so x to the 9th divided by x. Yeah, I'm not writing that step, but that would be the middle step here. Yeah, 1 times x to the 9th, and then 1 times x, and then you subtract the powers, you get x to the 8th. Minus 9x to the 8th ln of x, you don't really need the dot, all over x to the 18th. Okay, now watch this, one more step. Factor out the x to the 8th. There's an invisible 1 in front of this x to the 8th. So when you pull out the x to the 8th, you're left with the 1 and the negative 9. Do not combine them because the 1 and the 9 are not like terms. They don't both have the same variable factor. Right? The 1 has no variable factor, so that's it. And then over x to the 18th. And then finally, cancel x to the 8th, x to the 18th, and that leaves behind x to the 10th. Right? Remember, when you cancel variables, you subtract the powers. Right? If they're equal to each other, the powers are equal. When you cancel them, they just disappear because you're subtracting it from itself. But these are not equal to each other. So this is your final answer. Okay, so my philosophy with simplifying is you should always simplify, but there are some cases where you just skip it. In particular, if I announce in the problem that you don't need to do it, although you're still allowed to. If I tell you you don't have to, you can still do it anyway. You can say, you know, Dr. Jordan, I really enjoy the simplification process. But there's also a philosophical reason for simplifying. It teaches you skills and refreshes your algebra so that you'll be more prepared in the future. Okay, so notice all of these steps were a nice sort of walk through your history of algebra to make sure that you haven't forgotten some of the basic skills. Okay. So I sort of have a twofold approach to simplifying. And if I don't care, if I like it messy or I don't need it clean, then I'll just tell you, leave it alone. Put it down. Put it down before you break it. Sometimes simplifying something, you end up causing it to be more complicated. You don't achieve your original goal. Well, that's the quotient rule. Let's do a couple more examples and then we'll be done. So example 8. F of x is e to the x over x to the 4th. So find the derivative. Now again, I have f, so I don't want to name either one of these guys f, so I'll name that one u and I'll name that one v. And then in my shorthand, it'll be u prime v minus v prime u over v squared. That's my shorthand for that. All right, so u prime. Well, u is just e, so u prime is still just e. Times v, x to the 4th. And then v prime is 4x cubed times u, but u is just ex. And then v squared would be x to the fourth squared. So I've got x to the fourth e to the x minus 4x to the third e to the x all over x to the eighth. The order of the individual factor doesn't matter. You can leave it any way you like. Factor out the x to the third. Yeah. You can't factor out an x to the fourth because you don't have an x to the fourth here. So this is what's called the greatest common factor, x to the third. And so that goes out to the front. Again, an algebra review, when you have two factors with powers, the smallest power of the two is called the greatest common factor. Right? So if you have x third, x fourth, x third is called the greatest. It's the greatest common. And then again, cancel the x to the third with the x to the eighth, and that'll become x to the fifth. So your answer is x e to the x minus 4 e to the x over x to the fifth. I would also accept it this way. You could write the e to the x just one time because it appears in both factors. It doesn't really make the answer any easier though, so I don't require that. Okay. Let's do one that you don't have to simplify. Example 9. Something like this. I think we're ready for a exhibition of the formula without having to clean up our mess. And again, I'm doing this intentionally because in a future chapter, it's chapter 3, I'll review this one more time and then I'll say, don't simplify it. It's actually better if you don't. You get extra information by leaving it messy. Right? There's people that are kind of like that, right? That they have everything in a messy form, like maybe their office or their workspace or something, and to you it looks terrible, but they know where everything is, right? They can keep track of that mess. And sometimes it gets out of control and ends up on that show Hoarders, right? But hopefully we won't end up like that. All right, I like to just start off by squaring the denominator. All right. And then let's just go through the process. So we have the derivative of the top. Again, I like to say it, derivative of the top. So that's going to be 12x plus 4 times the bottom, 5x minus 4, minus the derivative of the bottom, 5 times the top, 6x squared plus 4x minus 3. If you're an auditory learner, the way I just talked through it, that's how I learn. I mean, I like visual stuff. It gives you something to look at while you're listening. But listening to how it sounds, I think, is very important because you don't always have the advantage of writing stuff down. But you do always have, your ears. You can listen. And even if your ears are, even if you're not hearing it, you're hearing it in your mind. Your mind hears things even that your ears don't hear. So derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. And you don't have to simplify it. Okay, got time for one more in this video, and I might actually get out of here under time. I always like to review some of the previous things when we learn a new technique. So earlier in this video, I reviewed marginal analysis just briefly. Make sure you don't forget that. And then now I'm going to end with reviewing tangent lines. So remember, when you take the derivative, you are finding the slope of a tangent line. So let's use this new tool to find the slope of a tangent line. Find the slope of the tangent line. Sometimes I make you find the whole equation, but in this one, I'm just going to say slope to the function at x equals 4. Okay. So again, it's the quotient rule that we just learned. The function is called f. So the numerator and the denominator, you could call them f and g, but it'll be confusing. So I would call them, a and b, or p and q, or u and v, whatever you like. Slope of the tangent line is the derivative, and then we'll plug this in at the very end. I would just wait. You could plug it in now, but it would probably be very messy. I usually wait. Let's do the derivative first. So again, we have the denominator squared. Derivative of the top is 3 times the bottom minus the derivative of the bottom, which is 2x, times the top. And there's no need to clean this up. You could just plug in whatever value you're given. So you're given 4. Go ahead and plug in 4. And if you want to do this on a calculator, you can. I'm going to try to do it by hand. So 4 squared is 16. 16 minus 1 is 15. Uh, 2 times 4 is 8. 3 times 4 is 12. 4 squared is 16. 16 minus 1 is 15. I'm running out of space. Here, let's go over here. I saved a little space up here. I got 45. So that's the 3 times 15. I've got 12 minus 5 is 7. Eight times 7 is 56. 8 times 7 is 56. And then the bottom is 225. 15 squared is 225. 45 minus 56, I believe, is negative 9 over 225. Simplify or reduce only if possible. It's not possible. 9 and 225 don't have, or do they? Oh, shoot. It is possible. I got to go one more step. I'm going to break out my calculator. 225 is divisible by 3. Oh, it's divisible by 9. 225 divided by 9. It's totally possible. Don't box it yet. So I got 45 minus 56. Oh, shoot. So glad I grabbed my calculator. I was trying to be tough. I have to admit it. Dr. Jordan was trying to show you how smart and tough he is by not using a calculator. And I almost screwed up on the very last example. I think I did that in my last video. You should read my comments. I wrote something down wrong at the very end and crash landed at the very end. So we are done. I'm glad I used my calculator. 45 minus 56 is not 9, it's 11. So that is the final answer. It cannot be reduced. And I stand adjourned. Do your homework. Learn some math. And see me next time. I'm Dr. Jordan. See you on the internet.